Hello again. This is Math321. I have to stop doing that thing and saying right. It's not very good. Right. I'm talking about polynomial interpolation. I will justify why polynomials should be used in a moment. First off, I'm going to define an interpolating polynomial. So, an interpolating polynomial for a function f from the real line to the real line is a polynomial. So that there exists x0 up to xn plus 1 xn with p n xi, so the polynomial p n reals p n xi equal to f xi. We don't need to know the function. In many cases, in a computer, functions are represented by some polynomial when you want to evaluate them. You won't see that so much because it is usually all handled in the background, but you could suppose that we've measured, or we have an estimate of the value of the function at xi, for example, in which case I'll often write this just as fi at xi to emphasize that the value fi was measured rather than evaluated. But I'll use the notation interchangeably a little bit, so just watch out for it. And the pointwise error function is the difference between these two things. If f is a polynomial and you've measured a sufficient number of points, Pn should be exactly equal to f. And that follows because we know that polynomials are unique if you have n plus 1. So an n degree polynomial is uniquely specified by n plus 1 points. So the lemma here is that Pnx and Qnx be any two polynomials of degree at most n, for which Pnxi equals Qnxi, and there are n plus 1 of these. Where the xi's are distinct. Then Pnx equals Qnx. So a line can be specified by n plus 1 points, assuming that the values of the function at those n plus 1 points do lie on a line, which is the reason why we're talking about degree at most n rather than saying specifically actually degree n. In some sense, I suppose if you're happy to say that a line is a polynomial of degree 2, but somehow degenerate, then this would also apply in that case. But anyway, the proof is left to you. That's an exercise. It relies on the fundamental theorem of algebra. So we have uniqueness, and we have an error function. We know what interpolation functions are. Now we come to the error result itself. So we let f, a function from the real line to the real line, and we want it to have a continuous n plus 1 derivative over some interval. We'll let Pnxi be the interpolating polynomial for the n plus 1 distinct points xi inside AB, and I allow the xi's to be equal to AB. Then for all x inside AB, there exists some zeta of x, and you can think of zeta as a function of x in the interval given by the minimum of x0 up to xn, and the maximum of x0 up to xn, so that f of x minus pn of x is equal to the pointwise error function, which is going to be wnx over n plus 1 factorial fn plus 1 zeta x, where wnx is equal to the product of x minus xi, I equals 0 to n. So by definition, Rn xi is equal to 0 for all I. And that implies that Rnx is going to be equal to x minus x0, x minus x1, all the way up to x minus xn times some other function. We can write this as wnx snx. So now we fix x inside our interval. Wow, we can take it inside the real numbers really. But we fix it, and we let f of z equal f of z minus the polynomial evaluated at z minus our wn at z times s of x, Sn of x. You should check that fn plus 1 is continuous. And that's because we have a polynomial, we have a function, and this is a difference between a polynomial and a function, which all have the appropriate number of derivatives. So that's fine. Importantly, we know that f of x equals 0 and f of xi equals 0 for all I, 0 up to n. You should check that as well. It follows just by definition, and remember what the definition of Sn and Wx is. Right. Generalized Rolle's theorem now implies that there exists some c inside the open interval, so that capital F n plus 1 c equals 0. And we may ask what this is. The nth plus 1 derivative of a polynomial of degree n is going to be 0. And when you think about what this thing is, the answer becomes it's the nth plus 1 derivative of our function z minus n plus 1 factorial Sn at x. And of course, that implies that for our particular c, Sn of x is equal to fn plus 1 c over n plus 1 factorial. The implication being f of x minus pn of x is equal to wn at x times over n plus 1 factorial times f n plus 1 c. So the c has a dependence on x, and zeta x is equal to c of x gives the result. I should have just read zeta to begin with. So that's our error result. So these theorems tell us that there exists a unique interpolating polynomial given a sufficient number of points, and we know what the error for that is. And a good question is, why should we use polynomials at all? Are there enough polynomials? By which I mean, can every function be appropriately approximated by a polynomial? And the answer to that is, it is. There are enough. Somehow polynomials get close enough to whatever function you're considering, and that is Weierstrass's approximation theorem. So f is a continuous function on AB. Then for all epsilon greater than 0, there exists some n which depends upon 0, is inside the natural numbers, and a polynomial of degree at most n, bigger than our capital N, so that for all x inside a, b, f of x minus Pn of x is less than epsilon. The proof of this is difficult. I'm only going to do, I will give a proof. I'm going to give a proof that's specialized to a particular case, however, and when you normally see proofs of this result, they don't use the same sorts of techniques that I'm going to use. But you should be aware that that this is a nice concrete construction of the polynomial Pn, and that's important, even though the functions I'm going to use are not very good, very well behaved numerically. So an important point here is that in order to define the Pn, we need to have quite a lot of points. We need to have measured the function f, and while there exists an n, so that we just need to measure it that number of times, or there exists a polynomial of degree bigger than that, this theorem doesn't really give us the tell us what the relationship is between n and capital N. The proof does say a little bit about it, but the point is somehow that in order to approximate f really carefully, we need to measure it at a lot of points, which is not so great. So this justifies the use of polynomials for interpolation, but doesn't really tell us a great deal about how do we choose the polynomial to reduce the error. I'll talk about that a little bit later when Chebyshev polynomials come up. So I'm going to assume that a equals 0 and b equals 1. If that's not the case, you can always find a transformation which maps the appropriate interval to that by a closed bounded transform, and you should check that. Yourself. So I'm going to find something called the modulus of continuity of function f at delta. And this is the least upper bound of the difference between f of x minus f of xi, where x and xi are inside the interval I'm considering, and importantly, their difference is less than delta. So this is somehow the modulus of continuity, where I measure between points that are less than or equal to delta distance from each other. And by assumption, because f is continuous, the modulus of continuity goes to 0 as delta goes to 0, which you should check and define. And if f is Lipschitz, so if f is Lipschitz, so C0 minus, C1 minus, then the modulus of continuity is going to be less than or equal to the Lipschitz constant times delta, which gives you an idea of what we're measuring and how we're measuring it. To complete the proof, I'm going to define some functions. So here's my beta nj's, and they're going to be nj over xj times 1 minus x n minus j. There's some conditions on these things that are worth knowing about. These conditions all follow by studying a plus b n, or the first derivative with respect to a of a plus b n, or the second derivative a plus b n, because of course the bnj's are factors inside here. So you study these, what you find out is that the BNJs for all x are greater than or equal to 0 on an interval, and that makes sense because x is between 0 and 1, and x is between 0 and 1, so these are positive and that's positive, so that's fine. We also discover that sum from j equals 0 to n of beta nj at x is equal to 1, which is important. That helps us to use these things to do interpolation. We also know that the sum times j over n over j beta nj of x's is equal to x, which is quite a cute result. And also importantly, we know that the sum over these things squared of the beta nj x's is equal to the following: 1 minus 1 over n x squared plus 1 over nx. All of these things can be exploited in order to get the relevant interpolation that we need. So I'm going to define something called the Bernstein polynomial of degree n. So the Bernstein polynomial of degree n of f evaluated at x is equal to the sum from j equals 0 to n of the value of f of x at j. Remember, we have our some points, and in this particular case jn is going to equal j over n, which are all inside our relevant interval, times my beta nj's at x. So each of these is degree n, and that implies that this is degree n, where I've chosen n to be bigger than my capital N. Right, so the rest of the proof is to show, so I claim that the difference between f of x and the Bernstein polynomial of degree n of f of x is less than or equal to 9 over 4 times the modulus of continuity of f n to the minus half. And you can always choose this to be as small as you like, because we know that that goes to 0 as n goes to infinity. So this tells you how the epsilon is really connected to the degree, but it's not in, somehow it's in an awkward, difficult, complicated kind of way. So let us consider this function. I'm going to rewrite this as the sum of x's minus the xj's, where the difference is less than delta. I suppose strictly I should say less than or equal to delta. fx minus fxj beta njx plus the sum over x minus xj, where these things are bigger than delta. Same thing, f of x minus fxj beta njx. The terms in the sum all followed from the definition, so you should check that you can do that. And I'm going to define this portion of the sum is going to be s1x, and this portion of the sum will be s2x. It's fairly clear that the absolute value of s1x is going to be less than or equal to the modulus of continuity, because that's what this is, and that's what this is controlling, absolute value, times the sum of the beta nj's over x over the appropriate things in here. Of course, that's equal to 1 from the properties I just showed you, so this is equal to the modulus of continuity, or less than or equal to the modulus of continuity. Great. Now I'm going to let j be such that the difference between x and xj is greater than delta. I'm going to study this situation so that I can get bounds on my S2. So here we have f of x minus fxj. But I can rewrite this f of x minus f of psi1 plus f of psi2 plus all the way up to some f psi p minus fxj. And I'm going to do this. I'm going to choose my p equal to the smallest integer, the largest integer smaller than the value inside this bracket. And the value inside this bracket, of course, is bigger than 1 by assumption. So p is going to be bigger than 1, which is great. And I'm going to ensure this, by making this particular choice for p, I can ensure that the difference between each of these differences, the sum of each of these differences, is less than my delta. That's pretty much ensured by this condition here. So this implies that the absolute value of x, f of x minus f of j, is less than or equal to p plus 1 times the modulus of continuity. And if you consider what p plus 1 is, this is going to be less than or equal to 1 plus x minus xj over delta times the modulus of continuity. And this, of course, is bigger than 1. Now the next step in the proof is to interpret what that means for S2. The modulus of S2 is equal to the sum, is less than or equal to the sum, x minus xj, greater than delta. And I have the absolute value of the difference between f of x and f of xj times my beta nj's x. From what we've just shown, this is wf delta, so that's the modulus of continuity of f for the distance delta, times the sum beta nj x plus 1 over delta times the sum x minus xj beta nj. And this is less than or equal to f, the modulus of continuity times, well, that's going to be less than 1. I mean, of course, it's going to be bigger than probably 1, exactly, because there will be some xj's, hopefully, who have distance less than delta from x. 1 plus 1 over delta times the sum absolute value. Well, absolute value will be certainly less than the square. Why is that true? Because the difference between these things is bigger than delta. This is going to be less than or equal to wf delta 1 plus, I put an extra square in to ensure that the squared is the appropriate thing, 1 over 4n delta squared. Now why is that true? That requires some careful thought, and it boils down to saying that x minus xj squared beta nj x is equal to x 1 minus x over n. Think about it from the conditions that we've given already. And this is less than or equal to 1 over 4n by just considering the maximum value. Right, so all of this implies that the difference between f of x and my Bernstein polynomial is less than the modulus of continuity times 2 plus 1 over 4n delta squared. And if we choose delta equal to the inverse of the square root, then we see that that cancels with the n, and we see that 2 plus 1 over 4 is equal to 4 over 9, which gives the relevant result. So the Bernstein polynomials are great, they're very good, but to prove this result, but they're not so great for actual interpolation, because the Bernstein polynomials don't actually interpolate through the specific values. They don't minimize error. They're numerically awkward because of the choice, the factorials involved, and they might involve a very large degree required to get low error. So in order to interpolate the polynomial exactly, we need Lagrange polynomials, which I will come back to.